All right, lesson 37. We are going to talk about the biological effects of nuclear chemistry, and this is the very last lesson. So a lot of conceptual stuff. You need to make sure that you've read through this, that you know it. Because I'm not going to read all of it to you, but do make sure you pay attention to the things that I'm not going to quiz you on or expect you to know. Get a drink of water. Okay. So the two most talked about uses of radioactive isotopes are probably energy production and weaponry. We have not spent a lot of time talking about weaponry. We just kind of have this, agreement in the world that we're not going to produce harmful weapons. Doesn't necessarily happen, but I don't know that, if this was a military college and you guys were military individuals taking chemistry, we probably should talk about weaponry. But for the most part, the majority of you are probably going to find yourselves in industry somewhere, teaching somewhere, working in the medical field or a health profession somewhere, or in research, like academic research. Or something in the in-between. Maybe not all of you are going to end up there, but I think most of your interest lies outside of weaponry. If it doesn't and you want to know more about weaponry, you can let me know and I will see if I can find some good information for you, because your textbook is just not the best source of weaponry information. Please get the cat out of the plant. The cat is in the plant. Scientists are also interested in using isotopes in medical, chemical, and biological research. So this is a really huge field. In fact, if you are wanting to know about a job, there are these people called medical radiologist technicians, which are trained to provide the isotopic drugs in your imaging. So pretty interesting field of science. But in research, I knew a lot of people who worked with radioactive chemicals in order to trace biomarkers in a process. And so that's kind of what we're going to talk about right now. So this process is called isotopic labeling. Okay? It's done by replacing an element of interest with a radioactive isotope. So when we replace the isotope or the atom with the isotope, they're going to act in the same way, but the isotope can be tracked through a mechanism or through imaging. Okay? So say, for example, you have, this is the citric acid cycle. Okay, thank you. The cat jumped out of the plant and knocked the plant over. I'm sure there's dirt everywhere. Okay, this is the citric acid cycle. You probably learned a little bit about it in biology. It's part of your breakdown of food metabolism after glycolysis. Okay, I'll fix it in just a minute, please. Let me finish. So the following figure shows the carbon balance of the citric acid cycle. How would it be possible to prove that 2 carbons in the CO2 molecules came from the oxalate instead of the acetyl-CoA? So it's asking, so if you see here, there's 2 carbons that are from the acetyl-CoA that are blue, and then you have the 4 that are tagged in orange, and one forms of CO2, one forms of CO2. So it's saying, how could we know that these CO2 came from citrate and not from acetyl-CoA? Because so here they're color-coded. There's no color-coded carbons. And so the main way to do it is to take something and replace the carbons. And so for the most part, we could tag the carbons in the acetyl-CoA. And if the CO2 comes from the acetyl-CoA, then the CO2 molecules will be tagged. If the CO2 molecules come from citrate, as this mechanism shows here, then the CO2 will contain carbons that are not tagged. Okay? So then we track the CO2 and see if the carbons are tagged or not. So that's essentially what they do. They have to plan ahead. They have to do intelligent decisions. They don't just say, well, let's just do this. They have to be intentional so that they make sure that they're tagging the right ones, or that they'll be able to determine it once they isolate it. Okay, so medical purposes. I told you guys that there would be, there is a table, and I would go through it. So here is the table with the most commonly, well, not most common, but some of the radioactive isotopes used in medicine. And so you have their half-lives. You can see that most of them are pretty short. I mean, they're a matter of hours, days. There's only one that's years, and that's the cobalt and the sterilization of medical equipment or for cancer treatment. That's probably the longest on here. The rest of them are a couple of days, okay, or hours or less. So why are most of the half-lives for the isotopes listed above fairly small? Well, the first part is that medical imaging is quick, usually quick. So the half-life can be smaller. So for example, you have the iodine 131, which is for thyroid activity. We'll see an image down below. You have technetium, which is imaging of various organs, bones, placenta location. If they want to do a calcium study, they could do calcium 47. Looking for tumors, location of ocular, brain, and skin tumors. The phosphorus 32, sodium 24 for blood circulation, fluorine for brain imaging and a bone scan. And so they're going to be fairly quick, and these scans are quick. But the other part is because there's a monitoring period after you have radioactive doses where you can't leave because you are going to be radioactive. So you can't leave the hospital with high levels of radioactive material because you are radioactive. Okay, so you are a source of radioactivity at that point. Radiation protection kits given out during the Cold War included iodine tablets. Why would these have been useful? We are not going to worry about that. It's just kind of a fun fact. Okay, so radioactive isotopes in the body can be monitored in a variety of ways. This is an example of a thyroid imaging using iodine. So a scintillation scanner is used for thyroid imaging using iodine. The picture on the right is a normal thyroid gland, and on the left, so on the right, normal, on the left is an enlarged thyroid. And the reason why you know that is because all of the dark spots in the images, so this would be, both are normal, is, looks like a smiley face now. Let's take that off. Both of these here are taking up iodine 131. And so iodine is, that's why we have iodized salt, because there's a deficiency in iodine in our diets, and so salt helps make sure it's in our diet, which is necessary for thyroid function. And so the radioactive iodine will be taken up by your thyroid, and here on the right hand image, left thyroid, they're right there by your neck. That one's large, and so it's taking up a lot of iodine, and we can see that very clearly here, that it is enlarged compared to the right, but then even more so enlarged compared to the image on the left. Technetium is used to study organs in the skeleton. So here's an example of a technetium scan. You can see that the joints where you have a high concentration around the joints, the knees, the ankles, the shoulders, the sternum, wrist, and things like that. Positron emission tomography scan can be used to study blood flow, oxygen use, glucose metabolism. It's useful PET to detect cancer, heart problems, brain disorders, other central nervous system disorders. They use fluorodeoxyglucose in the glucose test, and then many cancers show an increase in glucose uptake. Some people who have had cancers like lymphoma, which might be more systemic throughout your body, will have a PET to check all of their lymph nodes. So one entire body scan, instead of having something like an MRI of the brain or a CT of the abdomen, they're going to have an entire imaging done so that they can look at the entire body from top to bottom with a single imaging medication. Okay, so radiation units. So radiation can be measured in two ways. One is the units of exposure, so how much gets absorbed by an object or a being. And the other one is units of activity, and this is how much energy is emitted by the isotopes. So it's measuring what's emitted. The first one is measuring what's been absorbed. I'm going to be right back, part 2.